Now that we know about experimental probability and theoretical probability, let's compare the two together. So let's start, we're going to look at a dice simulation, but we're going to think about what happens, the possible outcomes when we roll two dice. So a pair of dice, which is very common in a lot of games, you roll two dice, and you know that your outcomes, when you add them together, you can get a number as low as 2, called snake eyes sometimes, or as high as 12 if you get 6 and 6. So let's just start. This table we're about to create here is one that you want to be able to reproduce quickly, because we're going to come back to it a lot throughout the course. So again, what we've got here is two dice. So if we imagine die number 1 down the left column and die number 2 across the top, then if we were to roll a 1 and a 1 and add those together, 1 plus 1 is 2. And so that's what would go into this square, this cell here. And if I rolled a 1 on die number 1 and a 2 on die number 2, then 1 plus 2 equals 3. So we're just adding them. So if we roll a 1 on the first die, then we can just add 1 to whatever we get in die number 2. And so we're just going to go up by 1 each time, aren't we? So we get 4, 5, 6, 7, adding 1 to each number on die number 2. The next row down, if we roll a 2 on die number 1, and then just go across adding 2 to each number on die number 2, so 2 plus 1 would be 3, and 2 plus 2 is 4. Again, we're going to go up by 1 each time. So there's a pattern going on to how we fill in this table. Now I'm going to add 3 to my green die each time, so I'd get 4, 5, 6, 7, 8, 9, and then add 4, so I get 5, 6, 7, 8, 9, 10. And notice how as I go down each row, I'm just starting at one number higher. So going this way, you'll notice it went 2, 3, 4, 5. So the next one's going to be 6, and then I go up by 1, and then 7, 8, 9, 10, 11, 12. So if I roll 2 die, and I think of them as different things, it might be helpful to visualize them as being different colored dice. You know, sometimes there's white dice, and sometimes there's red dice, and there can be other colors too. But imagine one of them being a white die, the other one being a red die, so that you can differentiate between them. So if there's 6 outcomes on one of the die and 6 outcomes on the other, there's actually 36 ways they can combine. And if you count up all the cells in here, if you count up all these different cells we filled in, there's actually 36 of those. But those outcomes repeat each other sometimes. For example, I can see that the number 7 actually shows up in every row. It shows up 6 times, whereas the number 2 only shows up once, or the number 12 only shows up once. So they have different frequencies of how often it comes up. So we're going to do a little graph here. We're going to show the theoretical frequency for the sum of dice when 2 standard dice are thrown. So on the bottom, we'll put our outcomes. So just across the bottom, I'll write 2, 3, up to 12. Notice I don't start at 1 because it's impossible to roll a 1 if you roll 2 dice. A sum of 1 anyway. 5, 6, 7, 8, 9, 10, 11, 12. And then we're going to put the frequency up the vertical axis. So in other words, how often each of these numbers comes up. And as I already pointed out, 7 seems to be the one that's most frequent. It shows up in each row. So, and that shows up 6 times. So that's the most we can get. So working backwards from having a maximum of 6 possible outcomes for a particular frequency of 6 for a particular outcome, then I'd fill in these other ones. So looking at the table, I'm just going to draw myself a little bar graph. So for 2, you can have a sum of 2 only one way. I can have a sum of 3 actually So I can have a sum of 3 two ways, right? I'll just leave that there. So there's 2 ways to draw to get a 3. So the frequency is 2 for the 3s. And there's 1, 2, 3, 4 ways to get a 4. Sorry, 3, did I say 3 ways? I've lost track. I feel like I said there's 4 ways to get a 4, but anyway, there's 3 ways to get a 4. There's 1, 2, 3, 4 ways to get a 5. And there's 5 ways to get a 6. And there's 6 ways to get a 7, as we already established. And then if I go to 8, there's actually 1, 2, 3, 4, 5 ways to get an 8 again. So now we're going back down. 7 was the most likely. And then if you just take a look, you'll see that there's 4 ways to get a 9. And there's 3 ways to get a 10. And there's 2 ways to get 11 and 1 way to get 12. So this is called a frequency distribution. Okay, so that is the way, so it's frequency here on this axis here, so the number of ways that each of these different outcomes can occur. So these are the outcomes down here. You know, these are the only things that can happen. We can get a 2, a 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12. And then the number of ways that each of them can happen. So they're not all equal. 7 is going to be most likely, followed by 6 or 8, followed by 5 or 9, until we get down to 2 and 12 are the least likely by far. That's theoretical. Okay, so these are theoretical frequencies. I mean, they're actual possible, that, you know, the way that it breaks down. But it doesn't mean that's what's going to happen if we actually do the experiment. So to do an experiment, I'm going to use a dice simulator. And so here's, I'd like you to follow along with this and do it on your own. So go to a new Google search and look up GeoGebra. And just go to the main page for GeoGebra. And if you look inside Classroom Resources, look up George Stir with a U. It may try to autocorrect for you. It did for me. And if I search for George Stir, then he's made a bunch of activities. I want the activity that's called Dice Roll Simulation. So I'm going to click on that. And it looks like this. Zoom, I guess that's as far as I can zoom out. Now I've messed up the scale. Let's try to bring it back in. I guess that's good enough. Alright, so you can see in the bottom left it says roll dice, and then beside that it says 1, 10, 100, 10,000. So if I click the 1, it rolls the die for me. It simulates rolling a die, and I got a 6 and a 2 for a sum of 8. And then you can see it's put a little bar above the 8 to show that we've got an 8 one time. And if I do it again, this time I got 2 and 2 for 4, and it graphed it for me. So I'm going to do this 36 times, because there's 36 squares when we theoretically think about them. So if I do 36 rolls, maybe my graph will look like the theoretical probability. This is experimental we're doing right now. So roll 3, I got a 6 and it's on the graph. And now I got another 8. So you can see that my bar for 8 has gotten a little higher. So that's 4 rolls. So that's just, I'm going to speed through them a bit more. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. All right, there's my experimental distribution. This is what I actually got from rolling the dice 6 times. So you see that my lowest number I got was a 2. There's nothing for 1, but we've already established that you can't get a 1 if you roll 2 dice. The lowest one is 2, and 2 turned up 3 times. But so did 7. Remember how many ways it was possible to roll a 7 compared to a 2? But they both turned up the same number of times, 3. That's interesting. 5 actually showed up more frequently than anything, and 12 didn't show up at all. So we're sort of all over the place here, all over the map. Let's see. So I'm just going to quickly, if I can, fill in this table so that I have something to make reference to, although I don't have to look. So we had, for 3, it was 1, what was it? 1, 3, 8, 5, 3 for the next ones. 1, 3, 8, 5, 3, 4, 5, 3, 1, 0. And for total, I'm just going to keep a running total. So you had 3, plus 1 is 4, plus 3 is 7, plus 8 is 15, 20, 23, 27, 32, 35, 36, 36. So that's my 36 rolls. And then if I want to sketch the distribution of actual outcomes, now, if you did this simulation, then yours might almost guaranteed is going to look different from mine. My highest frequency was 8. And if I just try to fill in these bars, big tall bar here at 5 for me. Now they should all be the same width, but you gotta allow me some human error as I draw them. Some of them are going to be a little wider than others. Alright, there's my graph. Let's compare these two. Clearly, they do not look the same. I mean, they do have one that's taller than the others, and they have shorter ones, but no, I think I'd be stretching it to say they have the same shape. No, definitely not. Why do we think that is? Well, the reason, spoiler alert, the reason is because it's experimental. So the second one is experimental. So one way you can think about this is theoretical is the way things should be, but experimental is the way things really are. And I don't mean it's always like this, not really are forever, but this is the way my rolls played out, the way they really are this time. If I was to do it again, they would really turn out to be something different again. But it's not the same from time to time. It changes from trial to trial. So rather than adding one at a time, though, let's start adding 100. We can, in GeoGebra, we could add 10 at a time, or 20 at a time. Sorry, not 20. 10 at a time, or 100 at a time, or 1,000 at a time. Actually, let's not jump straight to 100. Let's just play with it a bit. Let's add 10. So if I click the 10 button instead of the 1 button, there we go. All right, so I'm going to hit the 10 button, and it just did 10 rolls for me. Now I can't see the individual rolls on the die because it doesn't show me all 10 of them. But you can see at the top it says total rolls 46. And the bars, a bunch of the bars moved. Let's do another 10. Watch the bars. Keep your eyes on the bars this time. So again, a bunch of bars moved. And now I got 56. Another 10. Another 10. Another 10. Let's get up to 100. So I'm going to add 4 more. And then another 10 to get me to 100. There's 100 rolls. That looks a little bit more like my theoretical probability, right? Here's theoretical probability again. It's got the highest bar in the middle and the shortest ones on the sides. Well, I don't have the highest bar in the middle, but I do have the shortest bar on the sides now. Now let's try adding 100. So I'm going to click that third button down and actually add 100 rolls. So now I got 200. Okay. Highest bars are in the middle. 10 is also kind of high though. Let's add another 100. Okay. It's gotten a little bit worse rather than better, I think, as far as evening out goes. We've got 2 high bars that are higher than in the middle. Let's add another 100. Okay. 6 is the highest. Another 100. 6 is still the highest. Okay, now that I've got 600 rolls, this is the first time I've seen 7 actually be the highest bar, but it is now. Let's add another 100. Let's go up to 1,000. Okay, 7 is definitely the highest now. 800, 900, there's 1,000. Okay, definitely it's starting to look like my theoretical frequency distribution. Okay, let's just jump right to 10,000. So let's add 10,000 for a total of 11,000 rolls. Okay, now it really looks like it. So I'm just adding 10,000 at a time, and this is getting almost identical. I've done 111,000 rolls, digitally, of course. But at 111,000 rolls, 18,522 of them were 7s. The next closest was the 6s. 6s at 15,371. Interestingly, look, it's almost identical to the number of rolls of 8. It was also 15,363. It's only 8 different. And compare 5 and 9. Those ones are both in the mid 12,000s. Same with 4 and 10. Those are both in the low 9,000s. 3 and 11 are very close. 2 and 12 are very close. So there's something happening here as I add more and more rolls. So anyway, let's talk about that in a second, but let's actually answer the question. Keep adding cases until the experimental sums looks very similar to the graph of theoretical sums. Check. How many cases did you have to use? Started to look like it around 600, but really looked like it at 1,000. So around 600 if you're being generous, but maybe 1,000 rolls if you want to be more conservative. Explain what happens to the sums of the dice from experimental data compared to theoretical data as the number of trials increase. The experimental outcomes, the experimental probability, is going to get closer to the theoretical probability as the number of trials increases. as the number of trials increases. That is our key idea. So experimental probability, if you just do 1 or 2 trials or a small handful of trials, is very unreliable. But experimental probability can be very reliable if you do enough trials. Think about polling. If there's an election happening, there's professional polling companies that can be very accurate in their predictions of what people are going to vote in a coming election. But they don't just ask 5 people or 10 people or 100 people. They ask enough people, a lot of people, certainly not everybody, but enough people that their experimental probability, which is really just kind of what polling is in a way, or it's related to it anyway, is going to represent what actually happens. So increasing the number of trials is a good thing. Why is experimental probability not a perfect predictor of the outcome of a probability experiment? Well, it's still random. There's variability. What is usually necessary in order for experimental probability to reasonably agree with theoretical probability? A large number of trials, as already stated. And that's the takeaway from today's lesson. Take a look at the homework questions and good luck.